So as an example of the application, we're going to consider a pendulum at its equilibrium position, y equals 0 at t equals 0, so y of 0 equals 0. Stationary at its equilibrium position. Y prime of 0 equals 0. Of course, stationary at its equilibrium position means it's in equilibrium. But it didn't say in equilibrium, it said at equilibrium. So we want to be careful how we specify things. Then we exert a sudden impulse at, let's say, t equals 5. Why not? Okay. Then what we can say is, without going through the derivation and worrying about the units and so forth, we get the essence of it by y double prime plus y, which is your net force function, equals delta of t minus 5. Y of 0 equals 0, y prime of 0 equals 0. And we solve this. And really the only way we've got to solve this is using Laplace transforms. So we transform both sides. And we get an algebraic equation we can easily deal with. We get s squared times Laplace transform of y plus Laplace transform of y equals Laplace transform of t minus 5. Well, you might have forgotten the formula. I'll write it down big over here so we can refer to it. Laplace transform of delta of t minus t naught is e to the negative t naught s. Okay, so this is then just e to the negative t naught s. Okay, well, let's factor out the s squared plus, well, the L of y. We're going to get s squared plus 1 times the transform of y equals e to the negative t naught s. So plus transform of y equals e to the negative t naught s over s squared plus 1. Okay, well, then y is the inverse transform of e to the negative t naught s over s squared plus 1. And this is just the Laplace transform of 1 over s squared plus 1 shifted to the right t naught units. So that equals the sine of t, but shifted to the right t naught units. That therefore equals sine of t minus t naught, but also it's the sine of t for t greater than 0. Shifted to the right t naught units means you're going to have to multiply this by u of t minus t naught. So the result is just this. Okay, we have the sine of t function, and I'll go ahead and do that kind of lightly and try to figure out how I can do this with colors. Get something that contrasts a little bit. Okay, so we got the sine of t. Okay, when I did the t naught here, I mean, we have delta t minus 5. It's obvious that t naught is 5. So I could have kept that. I could have used 5 from here on. I just wrote down t naught without really thinking much. So sine of t minus t naught is sine of t minus 5. U of t minus t naught is u minus 5. The graph of the sine function has a period of 2 pi. So right here is the sine of 2 pi, which is about 6. T equals 2 pi, which is about 6, a little more than 6. And 6.28 on the scale of this graph is way too many significant figures. It's about 6. So t equals 5 is probably about here. Okay, so right there's t equals 5. So what do we have to do? We have to shift this graph 5 units. Okay, well, we shift the graph of the sine function 5 units, and we get a graph that looks like this. But of course, the sine function shifted 5 units can continue back here, continue back past t equals 0. And since we're measuring time from t equals 0, we don't need to go past t equals 0, but, you know, we would still kind of want to have this graph coming back here. I wasn't real careful with that. Okay, but we have the sine of t minus 5 times u of t minus 5. And u of t minus 5 is 0 from here to here. And then it's 1, so we just have the sine of t minus 5 starting at this point and then continuing onwards, so that our graph of the solution is going to be well, I'm kind of getting out of sync with my picture of the sine function. But anyhow, there it is. Okay. So this is, first the white function is this. The blue function, which is supposed to be right on top of the white function, is the sine of t minus t naught multiplied by u of t minus t naught. And of course, u of t minus t naught is 0 from here on. So there's our picture. I believe your book has a very similar example. Not sure how far they shifted. I think they shifted the thing 2 pi units. So it's very much like this graph, except it shifts over here so that the new graph is right on top of the old one. Okay. There it is. Now what's this mean? This means a pendulum's at equilibrium, and it's sitting there at equilibrium until you wrap it at t equals 5, and then it starts oscillating. Okay, so stationary, then it starts oscillating. And if it's an ideal pendulum, it just keeps going forever or until somebody stops it. Okay. One pretty straightforward application of the Dirac Delta, of the unit impulse. And really what you're saying is that applying this unit impulse, okay, whatever you do with this Dirac Delta function doesn't start having an effect on the system until you get up to your t naught time. Then there's an impulse, and now the motion of the system changes. So fairly easy to see if you go back to how that was derived and what everything means. It's fairly easy to see that that makes a certain amount of sense. The other thing is, of course, when you multiply any function times e to the negative alpha t, the effect is going to be to shift the graph and you know, as we've seen. In other words, you got the rule. I've written it up small here. That f of t minus alpha times u of t minus alpha is e to the negative, and I guess that's a e to the negative as times f of s. So again, fairly easy to understand. I don't guess there's anything else I want to say about it right now. Let's look at another example now of a pendulum where you slap the thing when it's at its extreme position. Now your text, I think, does that. I think the first example is actually much like this, except it's at t equals 2 pi, which is the end of the first period. I think the second example is at its maximum position. Okay, so if your position is positive position in this direction, it's out this way from equilibrium, and you give it an impulse here. Okay, I'm going to bring it back on the other side of equilibrium and give it an impulse, just to see how that works, and you can kind of compare that with the example in the text.